Good morning. Am I audible?
Yes, sir.
Yes, sir.
Thank you. I am planning to take an extra class on 19th March, 10 a.m. onwards, maybe of 1 hour. Is it fine with your current schedule? It's a buffer day. Is it fine? Yes, no. Okay, then I will have it.
Sir, on 19th, we also have a quiz starting at 11.
Whose quiz is this?
Call 226. Uh, Professor Arun Kumar.
Okay, then we can keep it from 9. Is 9 a.m. okay?
Okay, sir.
Sir, we also have HUL quiz. I don't remember the time exactly, but I think it's from 8 and up to what time it is, I don't remember exactly.
Okay, so think about the time on which we can take 19th March. Okay, suggest a time, right? You can also give me a time to take this extra class on 19th March. Okay, post this on Piazza. What time is comfortable to you? Okay, so let's start this lecture. In the last lecture, we were looking at all pass filter. All pass filter has a constant magnitude response. And this filter that we have considered, this one, will have such a phase response. I think every one of you must have worked this out. And now what experiment that we were doing is we were passing a music signal through this all pass filter and we wanted to observe some behavior of that. So this is what we are doing, and let us listen to these 4 files again. So music just as it is without any filter, right? Because remember, this all pass filter is only creating phase distortions. It is not distorting the magnitude, right? It's only creating phase distortions. So without phase distortions would mean that there is no filter. Let us listen to this music first. I have not included computer sound. So you have heard the original music file. Now let us hear the music file with phase distortions. So what we observed that the music is completely comprehensible, right? You can recognize this song, sound, everything, the music track, everything. So that means the phase distortions did not impact the music quality much. It created some noise, but that's not much. Now let us hear the speech without phase distortions and then with phase distortions.
Bad.
So this is without phase distortion, and now let us hear with phase
Bad.
distortion. So what we have seen is some sort of echo has popped in, but again it is not significant, right? In fact, there is an Ohm's law of music. Now this law you do not read in textbooks because it's not completely correct. But Ohm's law was that we hear only amplitude and frequency of sound waves. Okay, that means any changes in phase we do not hear. But that's not completely correct. You have seen that some sort of noise we have seen, right? So we hear phase distortions, but not much. Okay. So this is one law. Let us see if this law is completely valid. Okay, so we have seen that this is some sort of validity is in this law, but is it at all valid? Can we create certain situations in which this law is not at all valid? Okay. So now let us hear a complicated speech. We just heard a simple speech. Now let us hear a complicated speech without phase distortions.
Hello class. Abhishek Dixit is an awesome teacher.
Now let us hear the complicated speech, the same speech with some phase distortions. Okay, the kind of phase distortions that we have presented before.
Hello class. Abhishek Dixit is an awesome teacher.
So it seems that this Ohm's law is kind of correct, right? So for music signal also it didn't create very complicated phase, very complicated changes, and also for a complicated speech there are not much changes. Okay. Now let us hear out one more file where I'm playing out the complicated speech with phase reversal. Okay, here we are doing the phase distortions, but now let us do the phase reversal. Okay, what is meaning of phase reversal? Suppose we are having a sinusoid with some theta phase. So we have just changed the phase, right? So instead of this, we have changed the phase. We have reversed the phase. So instead of theta, we have simply reversed the phase to minus theta. Okay. So we had a file, a speech file, the same speech file. What we did is we have changed the phase at each frequencies. Okay. So now let us hear that speech and see whether you can even make sense of that speech. Okay. So now you see that phase reversals make speech completely intangible, completely incomprehensible. Okay. Phase distortions, on the other hand, didn't do much, but phase reversals completely spoiled the party. Now let us hear the music with phase reversal. Okay. So music also with phase reversal, it's completely intangible, incomprehensible. So the moral of the story is simple phase distortions, simply passing out through a filter like this, okay, didn't do anything, or at least didn't disturb us much, but phase reversals impacted significantly. Okay, so the question is, why is this? Right?
Excuse me, sir.
Why is this? Yeah.
So could you please show phase reversal like pictorial on a graph? How does it look like?
I don't have the graph at the moment, but let us assume that you have a signal Xn, and suppose we are expressing this in terms of Fourier series, because let us assume it to be a periodic signal. So typically this is the Fourier series, right, that we have seen of a periodic signal. Now AKs are in general complex numbers, right? So instead of AKs, I can also write it like this. Okay. So we have broken down this complex number into polar form, and this is the magnitude of this complex number, and whatever phase it has, I have got it like this. Okay. Now what I meant by phase reversal, suppose this is the Fourier series of the signal xn. Instead of this Fourier series, I am creating this Fourier series. Okay, so I have reversed the phase. From plus, I have just made it minus. This is the main meaning of phase reversal.
Okay, so like isn't will it be like what I heard when it was a phase reversal that uh, this hello world or whatever it was being heard at the end. Like, is it like that? Whatever is being heard first in the sound should be heard like last.
Yes, yes, exactly. So let us look at the technical reason for this, and that will help us get some ideas. So suppose xn has this Fourier transform. Okay. Now when we are looking at x of minus n, we have seen that this will have a Fourier transform x e minus j omega. We have seen this, right? This is one of the property that we know exists. Now, what does this mean in simple terms? Let us assume now my signal is composed of some sinusoids, okay? Just for example. So suppose my signal is this original signal. Now, when I am doing this minus omega, so instead of this, I will have cos of minus omega naught n plus 15, right? Just as an example. And you know that this could be written like this, right? So what you see is the phase is getting flipped in sign. Okay. What does this mean? This means that a phase flipping normally corresponds to the time flipping of the signal. Or look at it in another way. Suppose I have time reversed my signal. Okay. So instead of xn, I am doing x of minus n. I am time reversing my signal. Okay, I am flipping this on the time scale. Time reversing will do what? Instead of xc j omega, now my transform will be x of e minus j omega. What does this mean? This means that instead of omega naught frequency, now my frequency will move to minus omega naught. Okay, that will mean that now my phase will be flipped. Okay, just as an example. So when I am time reversing the signal, automatically my phases will get flipped in sign. Okay, or I can assume that the frequencies on by which the signal is built will show some phase flipping. What does this mean? This means that suppose I am considering, let us say now my phase shift is of 30 degree, right? From plus 15, this has gone now to minus 15. Okay. The phase changes. You might have also seen that it also corresponds to delay of a signal, right? So suppose my this sinusoid is at omega naught frequency, and I'm looking at what delay this sinusoid gets through to have a particular phase change. So if lower is my omega naught, if my omega naught is small, then the delay that this sinusoid shows will be much higher. Right? If my omega naught is small, then for delta phi phase change, the delay that my sinusoid shows will be much higher. So what might happen is, just as an example, I'm explaining this at a very intuitive level. Suppose my signal is built up of two frequencies. very close by. And these frequencies are very small. Okay. And this gets flipped by, let's say, phase changes here 10 degrees, and for this the phase changes what? Let us say 40 degree, some arbitrary numbers. Now because these frequencies are very close by and very small, what you might see is that this frequency, because I should have taken other example. So let us take this as this goes through a phase change of 40 and this gets a phase change of 10. Higher frequency gets a phase change of 10 and lower frequency gets a phase change of 40. Now what will this correspond to is this lower frequency will travel much far and this frequency will only travel by a small distance. So what you would see is earlier, if I am looking this on if I'm looking this like this, let us put it a time scale, but you have to understand this clearly. So earlier I am hearing suppose a word or a phrase of the music signal which is composed of just say 2 frequencies. So earlier let us assume that we are hearing this frequency first. Okay, and this is a lower frequency. And then we were hearing this frequency after some time, which is a higher frequency, slightly higher, but both of them are low frequencies. After phase reversal, what will happen? You will begin to hear this frequency first and this frequency after some time. That means the phase reversals will correspond to actually some sort of time reversal of a signal. Okay, and that's why everything becomes very cluttered and incomprehensible. Is this okay?
Yes, sir.
Okay. Now let us do the same thing on images. So what we have seen, let me recap everything from the music and speech. Music signal doesn't get too much distorted because of phase changes, as long as there is no phase reversal. Phase reversal is disastrous. Phase reversal will lead to some kind of time reversal. Okay. So that's why we hear the phase reversal in music and speech, but we do not hear the simple phase distortions. Okay. Now let us look what happens in the case of pictures. Suppose we have this image. Now so this image again has 2 parts, right? The magnitude part and the phase part, right? So suppose this is an image. Okay, consider this as a black and white image for simplicity, though it's a colored image. So suppose this is some form of a 2-dimensional signal. You can take the Fourier transform of a 2-dimensional signal, right? We have already seen this in case of the chessboard. Now Fourier transform will be a complex quantity. Now I can have the magnitude of that complex quantity and I can plot this. So this is the magnitude response of this image. Similarly, I can go and plot its phase. Okay, the phase response of this image looks like this. Now, when we look at this magnitude response and phase response, it is clear that you have no information about this picture. Okay, we cannot, by looking at individually these 2 things, you cannot tell us anything about the picture. So it is the magnitude and phase together that helps us imagine a picture. Now let me do one small exercise again for images. What I have done is I have taken any other picture, a second picture. I have taken its amplitude profile and I have created this picture using the magnitude response from a third picture or a second picture, and I have maintained this phase response. Okay, and I have created out this picture. Is there any confusion on what I'm saying?
Sir, what is this amplitude response and frequency response? Could you repeat?
So let me say, suppose you have an image. Let me give this number A. Suppose I have an image A. Okay. Any image is a two-dimensional signal. We have taken its Fourier transform, and we have, after taking its Fourier transform, we have got some magnitude response and some phase response. Okay. So let me put tilde here because A tilde is the Fourier transform of A. Then we have taken the magnitude of A tilde. So this is the magnitude response of the image. And I have taken the phase response, which is angle of A tilde. Okay. Now suppose I have an image B. This image B also has a magnitude response and a phase response. Okay. Now what I am doing is I am looking at an image C, which is this image C, where I have maintained this as the phase response and I am substituting the magnitude response of this. Okay. So by having this magnitude response and this phase response, I am constructing an image C. So image C is this. Image A. Image A is this. This is my image A and this is my image C. Okay. So what I have done is I have substituted the amplitude profile or magnitude profile from a different picture. Okay. In this thing. However, I maintain the phase response of the previous picture. Is this clear what I am doing?
Yes, sir.
Now, if you look at this image, could you make out that this image has got to do something with this image?
Yes, sir.
Yeah, there is some information. Of course, it will be distorted, but there is some information that this image is a distorted version of the previous image. That means what? What does this mean? This means that magnitude response does not play a very important role. If you can maintain the phase of the images, then the distortions are not significant. There are distortions, but they are not significant. Significant in the sense that you can make out that this image has to do something with the previous image. The phase response is really important for images, not the magnitude response. Now let me do one more exercise. I am now creating an image D, which I will show you. In that, what I have done is I have maintained this magnitude response. So this is maintained. And instead of angle A something, what I have done is I have sort of randomized it. Not randomized it, but let us say I don't know exactly what I have done, but let us say I have multiplied this with this. Okay. So I'm looking at image D where the magnitude response is maintained. I'm not changing that. The phase response I have multiplied with some number. And I'm looking at image D. Okay. Image D, if you see, is like this. Now, when you look at this image, can you have any sense that this image has something to do with this image? No, right?
No, sir.
No, sir.
Yeah, so this image has everything that the image A has. Its magnitude is intact, phase is multiplied by some number. And now we have an image which is completely different from the original image. Whereas on this case, this has got magnitude response completely changed, coming from a different picture altogether. Its phase response is maintained. Now, by looking at this image, you know that this has got something to do with original image. So what is the message? Message is, for images, phase profile is the most important thing, not the magnitude profile. Okay. And now if you're wondering, in this image, the magnitude profile is chosen from which image? Right? Because we haven't said that. You will be surprised that magnitude response has been chosen from this image. Now this image has nothing to do with the original image, completely different images. So I am choosing the magnitude response of this image and substituting into an image B. And you see that image B has still got all nice information. Okay. So I think I have convinced you enough that for images, phase profile is most important thing. Now the question is why? Why do we see phase distortions in images and we do not hear the phase distortions in music? Why is that?
So because since images have position associated with each element, like each pixel probably or something. So when we distort the phase, those elements get shifted, like they get randomized. So let's say if the eye of the cat is somewhere, it will shift to somewhere else. So these things happen at very minute level, so we do not make out what the actual image was. Whereas
Exactly.
amplitude will only reduce the intensity. The
Yeah. Yeah.
the image.
Abhinav answer is correct, right on the money. And this is important for images. Suppose I'm looking at a line, just a simple image. It's a line. Now you see line as a line because all these components are connected together, right? All these components are connected together. Now when we do phase distortions means what? Different components will move here and there, right? Suppose we do phase distortions, what might happen? This may move here, this may move here, this may move here. And so now while looking at this thing, you cannot understand that the original thing was a line. Remember, phase distortions are always producing some sort of delays in the elements. Now when I do phase distortions just on a line, I will see its different components get scattered. And of course, you know that this has not, means you cannot make out that this has anything to do with the line. And that's why we are very sensitive. So we see an image as an image when its various components are intact. They are in some relationship with the other. If you change their positions, then of course you know that you will not see anything. Okay, so now let us do some maths. I think I have done enough demonstrations. Let us see some simple maths. So you know that the discrete time Fourier transform for a discrete time signal Hk is like this, right? Now instead of He j omega, if I look at He minus j omega, this by definition will be this. And you know that this quantity will be simply He j omega conjugate if Hk is real, right? If Hk is real, then this thing will be same as this thing. And when this thing is going to be same as this thing, what What is the interpretation? What is the interpretation if we have conjugate symmetry? What does this mean? It means that magnitude of Hej omega will be what? What kind of function?
Even.
Even we have seen all of this, so I will not repeat it. I don't. And the phase of Hej omega is odd. Okay, so Hk being real will mean these two things. All right. I think I have missed one slide. The order of the slide is not correct. So one message that you have to know is if Hk is real, then the magnitude response of the Fourier transform is even function and the phase response is an odd function. Same as in CTFT. Now, if cos omega naught n is an input to a linear time invariant system, we know that the output should be magnitude cos omega naught n plus phase of DTFT. Right? Similar to what we saw in CTFT. Nothing changes. Anyone wants any explanation on this? I am assuming that you know this because this is as same as in CTFT case. Any question? Yes or no? 2 answers, please.
No, sir.
Okay. Now, from Hn we can find Hej omega. The second thing we need to find is we need to find Hn also from Hej omega. Right? We have to complete the transform pairs. So using this equation, if given Hn, you can find Hej omega, right? But given Hej omega, can we find Hn? Yeah. What do you think? Can we find? Yes, we can find. That's why we are studying discrete time Fourier transform. So how to find this out? Let us see. So Hej omega is given like this. Simple. I can multiply Hej omega with e to the power j L omega. What is the motivation? Motivation is we know that what we are doing here. What is Hej omega? Hej omega is the inner product of Hn and e to the power j n omega. Right? This you know, Hej omega is the component of Hn along this direction. So if you have to construct Hn from Hej omega, you know that you should be looking into such quantities and see what you can do with it. Right? Hn you know will be some sort of has to do something with this. Right? Some sort of expansion needs to be done with this function. Okay, so this is the intuition. So we have taken discrete time Fourier transform multiplied by this. And what does this result in? This, right? Very simple. So now if we integrate this quantity within a period, why within a period? Why are we integrating this within a period and not from minus infinity to plus infinity?
Because it is a periodic function.
Exactly, because this is a periodic function. If you would have integrated this from minus infinity to plus infinity, then this integration would not exist. Right? You will get infinite values probably. So it makes sense only to integrate this between 0 to 2 pi, and let us see what happens. Do we get some answers? Okay. So we are taking this function and integrating with between 0 to 2 pi. So far it's fine, right? Now Fubini's theorem helps us, and we can swap the summation and integration. And I know that I could have written the previous equation like this. Now let us focus our attention into this quantity. What is this quantity?
Delta L n delta n. The L minus n.
Yeah. So this quantity, if remember L and N both are integers, right? So if L is same as N, then we simply get 1 here, and my answer will be 2 pi. If L is not same as N, okay, right? So we get, if L is not same as N, let us take some arbitrary thing just to get some insight. We get possibly quantity something like this. Now what is this quantity going to be? Remember, this omega is a periodic quantity, right? It's a periodic quantity. It lies between 0 to 2 pi. So then you can see that this, what does this mean? Is that this thing would be simply 0. This is an important difference, okay, which you have to keep in mind. So we know that if L is same as N, we get 2 pi, and if L is not same as N, we get 0. So basically it means that this quantity is 2 pi delta L minus N. So now instead of this, we substitute 2 pi delta L minus N. What do we get? If instead of this we substitute this, so this is only non-zero when N is same as L, otherwise this is 0. So we simply get HL 2 pi, right? Is this clear? So when N takes a value L, so this summation is with respect to with respect to N, and N takes all values minus infinity to plus infinity. Now for all other values of N, this quantity is going to be 0, right? This will only be non-zero when N is same as L, and then this will be 2 pi. So out of the multiple terms that we have in the summation, only one term will get picked up, and that is HL. Okay, and HL, you see, it will be multiplied by 2 pi. So we get this as HL 2 pi. Is this okay? I hope so. So we can write it like this. I have already done this, and this is same as HL 2 pi, and from here we get HN as 1 by 2 pi this. So I can also change L to N, not a big deal, just a change in variable. So now I have both the equations. So now it seems that we can go to HEJ omega from HN, and we can also go to HN from HEJ omega. And indeed, these are the transform pair equations. That means you can go from one domain to another domain. Okay.
Yes, sir.
All right. So remember that these represents valid transform equations, and the sufficient condition is, again, it's not a necessary condition. The sufficient condition is that either Hn should be absolutely summable or it should be absolutely square integrable, square summable. Okay. So these are the sufficient conditions, same as in CTFT. These are the sufficient conditions for these equations to be valid transform pairs. If these conditions are not satisfied, still these can be valid transform pair equations, right? So these are sufficient conditions and not necessary condition. Because this is a discrete time signal, there is nothing like Dirichlet conditions and there is nothing like Gibbs phenomena that we have seen in CTFT. Any question on this? No, I assume it's no. So now let us do some trivial. We will start with some trivial Fourier transform pairs. What is the Fourier transform of delta n? Everyone work this out. Be active, take a pen and paper and work this out, everyone. I need an answer from you.
One.
One, but does everyone agrees that the answer is one?
Yes.
Okay, let us see the answer. Answer is one, and it's very simple. HEJ omega is given by this quantity, right? Instead of Hn, we have substitute delta K. And you know that this quantity is simply what? This is 1 when K is 0. Right? At all other times, this is 0. So this is simply 1. Now, what is the Fourier transform of a to the power n un? Quick. These questions should be done immediately. So HEJ omega a to the power n un, n goes from minus infinity to plus infinity, e to the power minus j omega n, right? Un, instead of un, I can have the limit 0 to infinity. So this is summation n going from 0 to infinity, a e to the power minus j omega n. It's a GP, right? 1 upon 1 minus a e to the power minus j omega, right?
Yes, sir.
Yes, sir.
So this is the Fourier transform of a and un. You have to remember a and un has got a Fourier transform 1 upon 1 minus a e to the power minus j omega. Okay. What is the Fourier transform of this signal? So this is a rectangular signal. So let me plot this. My drawing is not very good, but so let me assume this is n1, this is 0, this is minus n1. So this is 1 here and everywhere else this is 0. Okay. So this is some sort of rectangular signal, right? In case of continuous time Fourier transform, you have seen that this rectangular signal, continuous time rectangular signal, what Fourier transform a continuous time rectangular signal has?
Sync.
Why just one answer? What Fourier transform a continuous time rectangular signal has? Everyone just shout. What is the answer?
The sinc function.
Harihar, what is the answer?
It's the sinc function.
Why are you so quiet? Everyone must know that the Fourier transform of a rectangular function CTFT is a sinc function. Now we have a discrete time rectangular function. What should be its Fourier transform? Again, quiet. What should be its Fourier transform? Prahlad, what should be its Fourier transform?
I don't know, sir.
But I have already told you, right? So if CTFT, continuous time Fourier transform of a rectangular function, is a sinc function, what should be the DTFT, discrete time Fourier transform of a rectangular function? Anyone else who wants to make an attempt?
So it is kind of a sinc function because it is summation of cosine.
So everyone must understand that the answer sinc function is incorrect. First of all, why the answer can't be a sinc function? Anyone?
Because sinc has limit at t equals to 0, whereas in discrete, I don't think there would be any case of limit or something.
No. That's not the correct, because sinc function is an aperiodic function, right? Whereas the discrete time Fourier transforms are always periodic. So anyone who thinks that the sinc can be the correct answer is actually incorrect, because of the primary reason that discrete time Fourier transforms are by definition periodic, whereas sinc function is an aperiodic signal, right? So the answer can't be sinc. Okay, so the discrete time has this difference with this continuous time case. Its Fourier transforms are always periodic. Remember this difference in mind. So let us look at the answer. It's 1 when n goes from minus infinity to, when n goes from minus n1 to plus n1, and at all other time instances it's 0. So we can write xc omega like this. And you know how to deal with such a summation, right? So this is of the form a r to the power n minus 1 r minus 1 of this form. So r here is e to the power minus j omega, okay, and a here is e to the power j omega n1, right? Minus and minus n1, that makes it plus. The number of terms here is 2n1 plus 1. Okay, so e to the power minus j omega 2n1 plus 1 minus 1. You know this, right? Now you can play out the usual trick that we play. So let us look at this term first. We pull out what? Let me show this for one case. So this lower term, if I can pull out e to the power minus j omega by 2, it will have like this, and this is simply minus 2j sine omega by 2 times e to the power minus j omega by 2, right? So this can be written like this. Okay, simple. arithmetic exercise. So instead of this, we write it like this. Instead of this, we write it like this. And then we can simplify this and we can get a nice answer like this. So it's of this form, sine by sine form. Okay. So just you have to remember that this is of the form sine omega, number of terms, total number of terms, right, divided by 2 and divided by sine omega by 2. Xc j omega is of this form. So it's not a sync signal, but it is something like a sync. Okay, and this signal is periodic in 2 pi. Clear? So we can plot this also. I have plotted by my hand, so it's not a perfect picture, but you can see that this is a periodic signal, behaves something like this. Okay, not to the scale. And I'm plotting this for n1 equals to 2. Let us see some more, and I hope you are absorbing all of them. If Xc j omega is delta omega, what is Xn?
One.
One.
Both answers are incorrect. Do you want to revise your answer?
2 pi.
1 by 2 pi.
No, 2 pi, only 2 pi.
No, it cannot be 2 pi, right? Because Xn, what is the formula? 1 upon 2 pi. 0 to 2 pi. Xc j omega e to the power j omega d omega. Right? If we blindly have put delta omega, then you know that this will be 1 upon 2 pi. Okay. So, but this question is incorrect actually. This is not the correct question. Why is this not a correct question? Because Xc j omega cannot be delta omega. That is the first thing. Delta omega is not a periodic signal, right? Xc j omega, this is important, and that's why I'm emphasizing it again and again. Xc j omega has to be a periodic signal. If someone gives you Xc j omega aperiodic, that means it's not correct. Okay, so keep this in mind. Say instead of this Xc j omega, if my Xc j omega is this, is it periodic? Yes. So now we have impulses. 0, 2 pi, 4 pi, and so on and so forth. This is a periodic signal. So Xc j omega has to be periodic. This is a periodic signal. Now for this signal, you can find Xn. Right? So Xn, if you work out, because we only have to take Xc j omega within a period. Okay. That's why we get the answer as 1 by 2 pi. Okay, but the minor error in the first question was it has to be a periodic signal. Okay. So if Xc j omega is like this, Xn is 1 by 2 pi. And if Xc j omega is like this, 2 pi times this, then xn will be 1. Okay, any question?
So when we took within a period, what did you take m? Like, will we
M is
consider
some
0?
integers. M is some integer. 0, 1, 2. Okay. It's not some integers, it's all integers actually. So I should have mentioned this. M belongs to set of integers.
Sir, one doubt I have. So when we were talking about the magnitude response and the phase response, so those were the magnitude and phase of the frequency response, right? For the
Yeah.
image and picture and the, yeah, okay.
Any question on this part?
So here the like integration limits are from 0 to 2 pi, which
Yeah.
like not necessarily include the value at 0. So will the integral be like, we definitely tell that it is 1?
In this limit, so we are integrating within a period. Okay. So instead of 0 to 2 pi, you could have chosen anything, right? For example, minus pi to pi or pi to 3 pi. Okay, you can choose any period, right? This is just example of one period, 0 to 2 pi, but you could have chosen any other thing. Now, when I am choosing 0 and 2 pi, so remember that if you are including 0, then you should not include 2 pi. If you're not including 0, then you have to include 2 pi because this is a period, one period. Okay.
Yes, I understand.
And if you're getting confused, then it's easy. You just take minus pi to pi.
So, but in this case, if we include 0 and not 2 pi, so shouldn't it be half like?
Why?
Because we would have only delta omega integral from 0 to 2 pi.
So this is 1 by 2 pi. So you are saying 0 to 2 pi and you are getting confused, right? You're
Like
getting
if we
confused.
don't include 2 pi.
Just a minute, just a minute. Yeah. So now you are saying that because my delta omega is a nasty function at 0, so you get an ambiguous answer. And if you are if you feel that this is an ambiguous answer, best thing is, so let me draw the picture. So there is an impulse at 0 and there is an impulse at 2 pi. So basically the first thing is you have to integrate this over a period. So if you are including 0, you should not be including 2 pi. If you are not including 0, you should include 2 pi. Okay. But of course, because impulse is sitting at these places, the answers might be ambiguous. And then it is best to take this as a period. No ambiguity, minus pi to pi. So you have got this in this completely.
Okay, you got it. Thank you.
Okay, so we finished this lecture here, and next lecture we will do some more Fourier transform pairs. Thank you.
Excuse me, sir.
Yeah.
I have a doubt regarding the project. So will it be a guide? Like, is it a guided project or how do we go about it? Like, just a brief idea.
So you have been given a TA, right? To talk
Yes,
to.
sir.
Are you
Yes,
not getting answers from that TA?
I did not ask that.
So you have to ask him, right? So you just explain him what is your project and what should you do in that project. If you have any
Oh,
doubt, he will guide you.
thank you.
Make use of the TS.